in this method, okay, I want to generate with respect to t. I believe t lie between negative h and h. Okay, now mathematically speaking, when I write this is moment. I got a random variable s, and I want to generate moment with respect to t, and t lie between that and that. Now, if this is defined as this exponential raised to power this, okay, this is the definition of a moment generating function. Okay, it is expected value of exponential raised to power ts. Okay, now if you take a look at what I have right now, I'm going to do something here. Okay, now if x is a discrete random variable, okay, now mx of t is actually going to be summation, right? Whatever here, right? And the probability distribution. Okay, so what am I trying to say now? This gives the moment generating function of a discrete probability distribution. That is why you got a sum, you got a phase. Does that make sense? Now, when you take a look at this guy, now I want to do something. Okay, what is the zero moment? If you really want to know, if you derive a moment generating function from a given probability distribution and you want to know whether you are right, you know what you're going to do? When I plug in 0, mx, when I plug in 0, okay, when I plug in 0, this is going to be that f of s. Oh my God, that's going to be 1. And what is this? What is the sum of s? 1. Does that make sense? Sum of a probability. So what I'm trying to say in a sense, okay, moment generating function, okay, the zero moment now, moment generating function is going to give you 1. So I can give you different probability distribution, and I ask you to derive the moment generating function. And you know what? After deriving the moment generating function, okay, we can actually use the idea of calculus to derive what we derived the other time. First moment, second movement, third movement, fourth movement. But if I want to do first movement, I'm going to do the first derivative. If I want to do second movement, I'm going to do the second derivative. If I want to do the third movement, and so on like that, oh my God, I want to call me right now. Let's say, for instance, I want to do d dt ms of t that I'm actually going to call m prime s of t. Okay, if I want to call me now, I want to differentiate. I'm differentiating with respect to t, right? You know that this is going to be x e raised to power ts f of s. Who doesn't understand that? Okay, now after differentiating that, please, I need you to listen now. If I wanted to get the first moment using the moment generating function approach, after doing the first derivative, do you know that expectation of s is the same thing as d dt mx of t, where t equal to 0? So right now, I'm actually going to look at my first derivative. Wherever I see t, I'm going to plug in 0. This is going to be this f of s. Oh my God. This is now going to be this. And what is that? That is the expected value of s. Look at that. Expected value of s is summation s f of s. Is that not beautiful? Do you have any question? Do you get stuck? Is anybody? Do you have anybody that gets stuck who doesn't understand that? Okay, which means if you derive the moment generating function and you plug in t to be equal to 0, that will automatically give you the first moment. And don't forget, the first moment about origin is the same thing as the mean. Does that make sense? Now, let's do the second derivative now. Let's do the second derivative now. D squared mx of t dt squared, okay, which is m prime x t, okay. Now I want to come here now because I've differentiated that before. Differentiated this again. It's going to be this s squared, this f of s, okay. Now what I'm trying to tell the world right now. So this guy m prime s of 0, okay, is going to be this guy. Oh my God, after putting 0, what is this? This is the expected value of s squared, which means the second, the second order of the moment generating function after plugging 0 will give you the second moment about the origin. Look at that. That's as beautiful as that. I can go all the way. Now, because if I look at this now, I'm going to generalize. Let's generalize right now. So d dt, okay, in our term, okay, generalizing it right now. Okay, generalizing it right now. Okay, m r x of t. Okay, of course, what are you actually expecting? Okay, so when you take a look at what we have, so this is just basically going to be that at the end of the day. After initially it's going to be e raised to power ts f of s. Okay, it's actually going to be that because when you have this one initially, when you differentiate it once, s is going to come down. Second time, another s, that would be s squared. Third time, s raised to power 3. R root time s raised to power r, right? Now, what I'm trying to say now, oh my God, this guy is the same thing as this guy. Isn't it? This is expected value of s raised to power r. It's a general form now. Okay? Now, you know what I want to do right now? I actually want to use one of the distribution. Okay? In the example, okay, take a look at example 13.1. Oh my God. Look at the example 13.1. What if I give you a distribution? And I said, derive the moment generating function. That is the first question. And I say, okay, use the moment generating function to derive the first moment, the second moment, the third moment, even get the variance. How am I going to do it? I need you to pay attention right now. Okay, I need you to pay attention right now. Okay, I want to, this is for the binomial. This is for the binomial. I'm quickly going to derive that. Is there any question so far? Okay, is there any questions so far? I want to say I've already uploaded my recordings up to Tuesday. Oh, today is what is today? Is it Wednesday or Thursday? Oh, Wednesday. Okay, I've done that up to Monday. I'll do the one of Tuesday because I was recording in parts, Okay, now we have a Bernoulli distribution that we've done before. Okay. In Bernoulli distribution, you have this guy. S start from 0, 1. Okay. And somebody said find MGF. That's moment generating function. Then find what is the expected value of x, what is the expected value of s squared, and the variance of x. Please, I need it to be focused. Now, I want to find the moment generating function first. Don't forget, because Bernoulli is a discrete random variable, I'm actually going to do e raised to power tx equals summation e raised to power ts f of s. Don't forget this guy. I can simply write that as f of s. So right now, I'm actually going to write ETS. What is f of s right now? P raised to power s q1 minus s. Okay? Now, s start from 0 to 1. Okay? Now, you see what I have right now? Okay, now, when you take a look at this guy now, I can actually do this. P E T or raised to power S Q 1 minus S. Right? Algebra. This and this carrying S. So can also do that. Okay, you're actually gonna see what we're doing now. Okay, so far so good, right? I'm trying to find the moment generating function of my time is I'm quickly gonna rush that. So of course we still have it tomorrow as well, so we don't have any issue. Okay, now if you take a look at this guy now, the moment generating function, okay, when s equal to 0, I'm going to have PET 0 Q 1 minus 0 plus PET 1 Q 1 minus 1. Is it not easy? Just so, Take a look at that. Plug in X 0, plug in 1. So there's going to be 1 here. There's going to be Q plus. This is going to be 1, right? And I got this. Okay, anywhere in the world, this is the moment generating function of Bernoulli distribution. I can also rewrite Q. Don't forget, Q can also be 1 minus P. That's what you see here. You see that? Oh, sorry, you see that? Okay, now, if I ask you to derive this, how are you going to know you are right? Oh, to know I'm right, if you want to check, we expect this to be equal to 1. If you derive any moment generating function for any distribution, if you really want to check whether you are right, okay, because if you are wrong, if you try to differentiate what is wrong, you're also going to have a wrong expression. Okay, right now